Hello, I am Brielle. Welcome to our Thermodynamic project. So today we are going to talk about the Rankine cycle. Here are the names of the people who contributed to this project. Here is the outline. So we are going to start by introducing the inventor of the Rankine cycle, then defining the Rankine cycle itself as well as its enhancements and applications. William John McCoy Rankine, a Scottish engineer and physicist and one of the founders of the science of thermodynamics, particularly in reference to steam engine theory, was trained as a civil engineer under Sir John Benjamin McNeill. Rankine was appointed to the Queen Victoria Chair of Civil Engineering and Mechanics at the University of Glasgow. One of Rankine's first scientific works was a paper on fatigue in metals of railway axles, which led to new methods of construction. Also, his Manual of Applied Mechanics was a considerable help to designing engineers and architects. In soil mechanics, his work on earth pressures and the stability of retaining walls was a notable advance, particularly his paper on the thermodynamic theory of waves of final longitudinal disturbance. In addition to that, his classic Manual of the Steam Engine and Other Prime Movers in 1859 was the first attempt at a systematic treatment of system theory. William worked out a thermodynamic cycle of events, which is the so-called Rankine cycle, used as a standard for the performance of steam power installations in which a condensable vapor provides the working fluid.
Hello, my name is Ali. I'm going to be continuing with the Rankine cycle and its application. The Rankine cycle was named after him and describes the performance of a steam turbine system, though the theoretical principle also applies to reciprocating engines such as steam locomotives. In general, the Rankine cycle is an idealized thermodynamic cycle of a constant pressure heat engine that converts part of the heat into mechanical work. In this cycle, the heat is supplied externally to a closed loop, which usually uses water as the working fluid. In an ideal cycle, the system executing the cycle undergoes a series of four processes: two isentropic processes alternated with two isobaric processes. The first isentropic process is a compression. The liquid condensate is compressed adiabatically from state 1 to state 2 by centrifugal pumps. The liquid condensate is pumped from the condenser into the higher pressure boiler. In this process, the surroundings do work on the fluid, increasing its enthalpy and compressing it. On the other hand, the entropy remains unchanged. The first isobaric process is a heat addition. Between state 2 and state 3, there is a constant pressure heat transfer to the liquid condensate from an external source, since the chamber is open to flow in and out. The feed water is heated from the boiling point of the fluid and then evaporated in the boiler. Now, the second isentropic process, it's an expansion. Steam from the boiler expands adiabatically from state 3 to state 4 in a steam turbine to produce work and then is discharged to the condenser. The steam does work on the blades of the turbine and loses an amount of enthalpy equal to the work that leaves the system. Again, the entropy remains unchanged. The second and the last process, which is an isobaric process, it's a heat rejection. In the heat exchanger, the cycle completes by a constant pressure process in which heat is rejected from the partially condensed steam. There is heat transfer from the vapor to cooling water flowing in a cooling circuit. The vapor condenses and the temperature of the cooling water increases. The basic Rankine cycle can be enhanced through processes such as superheating and reheating. In the diagram, the heat addition is continued past the point of vapor saturation. In other words, the vapor is heated so that its temperature is higher than the saturation temperature. This does several things. First, it increases the mean temperature at which heat is added, thus increasing the efficiency of the cycle. Second is that the quality of the two-phase mixture during the expansion is higher with superheating so that there is less moisture content in the mixture as it flows through the turbine. This is an advantage in terms of decreasing the mechanical deterioration of the blading. A comparison of the Carnot cycle and the Rankine cycle with the superheating is given in figure on the right side. The maximum and the minimum temperatures are the same, but the average temperature at which heat is observed is lower for the Rankine cycle. In order to prevent having moisture in the turbine, one can heat again after an initial expansion in a turbine, as shown in the figure on the left side, which gives a schematic of a Rankine cycle for space power application. This process is known as reheat. The main practical advantage of both reheating and superheating is the decrease in moisture content in the turbine because most of the heat addition in the cycle occurs in the vaporization part of the heat addition process. And lastly, we're going to see one of its most popular application, and it is nuclear power plant. In a typical design concept of a commercial boiling water reactors, the following processes occurs. So firstly, the core inside the reactor vessel creates heat. Secondly, a steam water mixture is produced when very pure water moves upward through the core, absorbing heat. Third, the steam water mixture leaves the top of the core and enters the two stages of moisture separation where water droplets are removed before the steam is allowed to enter the steam line. And last, the steam line directs the steam to the main turbine, causing it to turn the turbine generator, which produces electricity. Thank you.